Hi, everyone. Thanks for having me here today. As David said, my name is Jaime Lien. I'm a co-founder and head of machine perception at a startup called Archetype AI. Today, I'll be speaking about Newton, which is our foundation model for physical AI at scale. I think I speak for many people here when we're very excited for physical AI. This is just a screenshot from one of Jensen Huang's keynote speeches this year, where he showed that physical AI is the next big step in AI's evolution, starting from simple perception AI all the way to generative AI, which is taking the world by storm. Today's there's agentic AI, and what we're really looking forward to is the combination of sensors and physical world data with the ability to imbue artificial intelligence for physical AI at scale. At Archetype AI, we see physical AI slightly differently, though, from the rest of the industry. While a lot of companies and businesses and industries are thinking about physical AI for robots, that is, AI that helps robots navigate the physical world, we at Archetype are very interested in physical AI for humans. And what we mean by that is artificial intelligence that can help humans discover insights about the physical world, and humans be able to use that in order to solve hard problems in our world around us. So our founding team came from Google, where we pioneered deep learning and AI techniques for interpreting physical behaviors from very complex sensor data. These include things like pico radars, which we used for sleep quality detection or recognizing gestures at scale. And what we found, which I think is a finding of many people who work with the sensors in the real world, is that physical sensor data, especially when deployed in the real world at scale, is often complex and very hard to interpret. It often requires subject domain experts to actually interpret the sensor data into meaningful insights about what's going on in the world. Not only that, but physical world data from sensors is highly multimodal. There's a huge long tail of sensor modalities which aren't addressed by AI techniques today. And the ways that people address them are largely fragmented. So it's very hard to fuse and incorporate all this sensor data at scale. And so because of this, we've seen that classical ML techniques are not really economically viable for solving all of these physical world problems. We see this explosion of thousands or more bespoke single-purpose models that have to be developed one by one. At Google in particular, we found that even using the same sensor, every time we change the device or the use case, it would require a team of ML experts to redevelop this problem and redevelop the model in order for it to work. These solutions are very expensive to develop, as I mentioned. They're expensive to manage, and many times you have to train them from scratch for every single new use case. And because of this, there's this long tail of sensor data, long tail of applications that remain unsolved by classical ML techniques. So what I'd like to introduce today is Newton, which we've developed as a general foundation model for sensor data and for understanding the physical world. Our goal with Newton is to generalize one single model that can handle hundreds of different sensor types. And on top of this, be able to build thousands of different use cases with very little to no fine-tuning. So we're leveraging this concept of foundation models that today people are applying to natural language and LLMs. But in our case, we're applying to sensor data and all of these different modalities of sensor data that are already existing in the world today. We see this as a viable solution at scale because it means you can build all of these solutions very quickly with natural language. It means you have a pre-trained AI model for understanding sensor data out of the box, and you can fuse together many different sensor modalities along with contextual information in order to provide semantic meaning to these sensors. And so we're deploying this within what we call a physical AI platform. The model is at the engine of this core platform, but it's able to take in streams of different modalities of sensor data. It's able to convert these through the model into meaningful insights and general capabilities like behavior understanding, anomaly detection, and then summarize those into customer-specific applications that people can very easily deploy into the real world at scale. So the key point here is that our model, Newton, is able to translate signals from sensor data into meaning and human-interpretable insights. And the way that we do this is in this core architecture, Our Newton model is really founded on two main components, one that we call a physics world model and one that we call a semantic world model. And the main aim of these two components is A, with the physics world model, to learn without any human biases a physically accurate encoding or representation of real-world behaviors. And then with the semantic model, be able to translate that understanding and representation of the physical world into human interpretable meanings. So from these two components, both individually and in tandem, we can derive any number of use cases, including things like forecasting, multivariate analyses, anomaly detection, classifications, and these are all on the physical, numerical analytics side. But also these semantic interpretations that I described, things like descriptions or explanations or alerts, things that translate these physical and objective measurements into human interpretable insights and meaning. And the powerful thing here is that all of this data, both the physical measurements and the contextual information through natural language, are combined into one unified embedding space. So they share a representation. What this means is that people can very easily interact with this representation through natural language in order to steer the model to do what you want and extract the type of insights that you're looking for. So very briefly, I'll cover some of these main components, starting with this physics world model. We published a paper at the end of last year explaining our approach to this physical world model, being able to learn underlying physical evolutions and physical behaviors purely from sensor data alone. And our goal here was to be able to develop one general model for physical world processes where you could train it on a diverse but sparse set of observations from the world, and then have it generalize to sensor modalities and physical processes that it has never seen in training. So this is the ultimate goal because it means that you don't have to build a narrow, tailored data set for every single sensor modality or every single use case that you want to apply. Instead, you can have one model that's learned across a broad set of sensor modalities and then apply it to sensors and use cases it had never seen before. So very brief high-level architecture. It's a transformer-based encoder model. And basically, we trained it on a large cross-modal, cross-domain subset of sensor measurements, almost 600 million sensor measurements from the real world. This was fully self-supervised learning, so there were no injected human-generated labels, no implicit biases, no human-generated equations that describe how the physical world works. Instead, this was all learned purely from data. And what we found is that training the model in this way, it actually develops an underlying representation of physical world processes that encodes how these processes change over time. And so here was a simple test that we ran where the model was deliberately withheld from training on accelerometer data. It had never seen before these types of hanging spring mass systems. But at inference time, the model, which had never been trained on this data, was able to forecast accurately not only this simple oscillatory behavior of a hanging spring mass system, but the chaotic behavior of a hanging elastic pendulum, which is very sensitive and non-regular in terms of starting conditions and the way that the process evolves. Here's another example where with the exact same weights, the exact same model, we applied it to a totally different physical phenomenon. So here we took two beakers of fluid and the temperature differential between them was converted into a current. And what we saw was this same model, without any changes to the weights, was also able to forecast this underlying physical process. And so this is very interesting because then we were able to extend this to more complex real-world processes outside of the lab. We looked at things like countrywide electrical consumption. We looked at the oil temperature of an electrical transformer, water vapor concentration in a city in Germany. In each of these cases, we found that the model, which had never been trained before on this data, was actually able to reconstruct and predict future evolution of these processes purely from the pre-trained weights, a pre-trained foundation model. And in many cases, almost all cases that we looked at, the zero-shot and fine-tuned foundation model was actually able to outperform a model that was trained specifically on the target data. So it indicates that by training on a cross-modal, broad set of data, observing the general world at scale, you can actually do better at understanding any specific process than if you observe that single process alone. And this really points to the power of the foundation model, that you can leverage this broad set of knowledge, broad set of underlying physics that you observe through a large number of sensor modalities in order to do well on any single task. And the key here is that this embedding space, this latent representation, actually encodes a wide variety of behaviors that to us as humans also make sense semantically. So here we see that the same pre-trained model with no human labels injected is actually able to cluster meaningful groupings of physical phenomena. For example, a gearbox, according to vibration data, we can clearly separate out one with a broken tooth from one that is healthy. Or with accelerometer data, we can clearly see groupings and clusterings according to different human behaviors. And because of this, we can use this physical model in order to do things like out-of-the-box clustering of sensor data. Sensor data, it has never been trained before, but able to do things like identify different states of a machine. In this case, a drill rig, and identifying when it's slipping versus when it's reaming versus when it's drilling. Or we can do out-of-the-box anomaly detection across a broad variety of sensor modalities. In this case, this was a wind turbine with 63 different modalities, and we're actually able to find anomalies not only in each single variant, but anomalies across combinations of those different signals. And again, model has never seen before this application, this sensor data, or this use case out of the box. And now let me talk a little bit about what happens and the power that we can imbue into AI when we combine this physical world model, data-driven and learned purely through observation, with the semantic world model that actually aligns with our human mental model of the physical world. So here's an example where we take that same model, we're translating radar data, which you see in the left-hand panel. So clearly this is objective measurement of radio frequency waves. And with a simple natural language instruction to the model, we can actually translate this sensor data into a semantic textual description of what is happening in the environment. This is an example of signal to meaning that we can get by combining the physical model of the world with a semantic understanding and natural language contextual information about the world. Here's another example where now we're fusing multiple sensor modalities along with textual context in order to do things like interpret the risk of fire safety and provide recommendations about what to do. So here we have radar data shown on the left, microphone data or audio data in the middle, and Newton is actually able to fuse these two together along with this natural language instruction in order to tell that there's a situation happening when a person is present and an alarm is going off and what to do in that case. So this is very powerful because there was no pre-programming of all of these generated responses. This is simply the semantic model interpreting what is going on as seen through these different sensor modalities and providing generative recommendations and interpretations of what's going on in the physical world. This ability to use natural language is very powerful because it provides the means and the interface for people to interact with physical AI and change its behavior dynamically. So here we see an example where we have an accelerometer embedded into a package. And now with this natural language instruction, we can have the model interpret what kind of types of classifications or meanings we want to extract from the sensor data and change it in real time. First, from something like transit status. Is the package in motion? Is it on its way to its destination, or has it been delivered? Versus package mishandling. Has the package been dropped? Is it likely that there's a risk of damage to the package? And all of this is with a single model that we can change simply by changing the natural language instruction that we provide. So you can see immediately how we can scale to many, many different use cases simply by changing these natural language inputs and context that we provide to the model. We've developed a paradigm that we call lenses, which is really an encapsulation of specific tasks and specific capabilities of the AI model so that people can easily build solutions around them. And our goal is to have this within a developer platform so that developers can very easily program these lenses or solutions with natural language and then connect them together with other platform components into full end-to-end solutions. And this means it's very easy to quickly and scalably produce these AI solutions to any number of use cases and problems. Here's a quick example where we very easily develop a senior care monitoring lens that fuses together an occupancy sensor data along with data about network traffic and then provides recommendations and alerts depending on a person's behavior and their usage of devices. So you can see that Newton actually provides an alert when an elderly person in the middle of the night wanders away from their bed. So this type of application would take many months potentially to encode and try to classify all the possible behaviors that might result from network usage as well as human behavior in the environment. And here's one final example where we show how on top of this physical ability to detect anomalies, we can actually interpret them into natural language explanations and diagnoses of these anomalies based on vibration sensor data in real time. So here we see the vibration data. Newton is not only able to detect that an anomaly has happened, but also able to explain what this means in context of this machine, where the gearbox is located, what the possible cause of the anomaly is, and recommendations about how to further diagnose or solve the problem. So I just want to close by saying we see at Archetype AI a huge opportunity here for physical AI. Obviously, our physical world is very complex, it's very dynamic. If we think about the world economy, about 80% of the economy is dedicated just to keeping the physical world running. Industries like transportation, construction, security, retail. And we see this opportunity now for combining sensor data along with AI that can help us to interpret that sensor data and make sense of the complexity in the physical world around us in order to discover solutions that will help us to improve the world and the way that we live within it. Thank you very much.